Besides solving inequalities using algebraic method, we can also solve inequalities by graphical method. So this is an easier way to comprehend solutions. We use graphing tools. So in this example, we are asked to use a graphing tool to sketch two graphs. One is a straight line given by x plus 2y equals to 8, and another graph that is given in blue that is given by a modulus function y equals to modulus x plus 4, which is in this case sketched over here. And we'll notice that what the question requires from us is really to find a portion of the graph that is the modulus graph is greater than the straight line. So when we talk about it being greater, we are talking about the portion where the graph is larger or above. So then if we just look at the coordinates that is given on the graph, we are now able to know then that it is going to be the portion of the graph that is less than -16 and greater than 0, both being inclusive because the question excludes the point of intersection. Another example to solve inequalities by graphing method is given here, and there's two portions to this question. We are going to first plot a graph of such and solve the inequality given over here. So we sketch two graphs, we plot two graphs over here for you, and the modulus function is the graph that is V-shaped, and the graph of over here y equals to 3 over x really is our rational function that you can see in red. So if the question now requires us to find a portion of the graph that is greater, which means we want the part of the straight line that is above the rational function. So we are talking about portion of the graph that is going to be from 1 and above, and 1 is really included in this case, and 0 and below and less than 0. So we also have to take note that because this involves a rational graph, it's always very important to check that denominator is considered and it cannot equals to 0. So that solution must be excluded. The second part of the same question requires us to hence write down the solution, and the only difference that you can notice from the first part of this question is it has a modulus x function. So we put a little note here that we recall a transformation that we had learned before, that if you do a modulus x transformation, what happens is we are taking this portion, this portion of the graph and doing a reflection about the x-axis. So there's a reflection. So the eventual graph that we are talking about, the eventual graph that is considered to be y equals to 3 over modulus x would be this portion that is in green, now highlighted yellow. So this is the portion of the graph that we are talking about. And if we want that portion of the graph to be less than the modulus straight line, we are talking about the solution set that really is below, and so this is the eventual solution set that we are talking about, whereby x is going to be less than -3, and over here x is going to be greater than 1, and if we check for the same condition in this case, we know that a modulus function is always positive, and it cannot accept 0, and 0 is not in our solution anyway, so it's really quite safe to include both ends, both -3 and 1.